Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I will discuss about CFD analysis of a single pass counterflow heat exchanger using SolidWorks flow simulation. And to find out its effectiveness, we will find out LMTD in the equation goal also, right? This is the model. It is already made using SolidWorks and the leads have already been provided. In this model, hot ethanol will be showing from this end with a temperature of 78 degrees centigrade, and cold water at 10 degrees centigrade will be passing from this cold water jacket. Okay, let's start it. We have to create the flow simulation environment with the wizard. So starting from wizard and providing the name of this project as single pass counterflow heat exchanger. Next, we're selecting the unit as SI system and temperature will consider degree centigrade. Then next, it is an internal analysis and we're considering heat conduction in solids. Next, liquids will take water and ethanol. Ethanol will be passing through the inner copper tube and water will be required as a coolant. Next, the metals, we are considering the inner pipe is made up of copper and the outer one is made up of brass. We'll take copper as a default metal and brass will be taken later on. Default outer wall thermal condition and roughness we are considering. Next, thermodynamic parameters. We have to take temperature. We are considering room temperature equal to 30 degrees centigrade and concentrations. We are not mixing ethanol and water. 100% ethanol will be passing through the inner copper tube, so its concentration will be 1, and from outside in a cooling jacket water will be passing as a coolant, so it will be separated. So initial condition, ethanol is having 100% concentration and water is 0%. Let's finish it. We have to go back to the system again. Initial conditions will see solid parameters. You have to check the temperature of solid. It will be 30 degrees centigrade. Okay, all conditions are done. Okay, now this is the computational domain, right? So the thing is, all parts of our model should be inside our computational domain. So what can you do is, this part we can make a little bit more, in which the leads should not be outside. Computational domain we can edit a little bit in such a way that all parts of our model should be inside our domain. Nothing should be outside. Okay, domain is ready. Now green check and we can hide this domain. Okay. Next, we have to see the fluid subdomain. So better allocation of these liquids, we can make one segmented view of this model. We can cut it from the front plane. Now let's provide fluid subdomains. Insert fluid subdomain. First of all, we'll take ethanol only, and temperature of ethanol will be 78 degrees centigrade. Ethanol will be passing from this copper tube. This is the location of ethanol. This is the fluid subdomain for ethanol. Okay, go and check. Next, I want to show the location of cold water. Again, fluid subdomains, insert fluid subdomain, it will be cold water. So we have to select water only, and the temperature of cold water will be 10 degrees centigrade. We have to locate it. Cold water will be passing from here. So this is a subdomain for coolant cold water. This is our complete model. Next, we have to provide material. Material, insert solid material, predefined. From metals, we have already selected copper. We'll provide again. Copper is selected as the inside material, and for the outer cooling jacket, you have to select brass. So copper, we have to select again material, solid material, insert solid material, predefined. We're considering alloys, and it will be brass. So select brass, but we can select it from the original model itself. Outer jacket, this is made up of brass. Grain check. So the two metals have been specified: copper for the inner tube and brass for the outer jacket. Next one, we have to apply the boundary conditions. For applying boundary conditions, it is better to select the segmented view of the model. Let's see it from the front plane. Now we have to apply boundary conditions, right? Boundary conditions, insert boundary condition. Let's the mass flow rate of ethanol will be 0.001 kg per second, and thermodynamic parameters is temperature will be 78 degrees centigrade, and substance concentration, it will be 100% ethanol and 0% water, right? We have to select the location of ethanol. Ethanol will be passing from this location, right? Grain check. Done. Next one, another boundary condition is required, that is for coolant. Insert boundary condition, and mass flow rate will be also same. We're considering 0.001 kg per second. Thermodynamic parameters is temperature will be 10 degrees centigrade, and substance concentration, it will be 100% water, and ethanol will be 0. So ethanol will be 0 and water will be 1. That means 100% water will be passing through this cooling jacket at 10 degrees centigrade. Now we have to select the location of cold water, right? It will pass through this end. Green check is provided. Now two more boundary conditions are needed, that is atmospheric pressure, right? So boundary conditions, insert boundary conditions. From this end, hot ethanol is passing, so this one will be acting as a second boundary conditions. For this one, it will be atmospheric pressure. Select this one, green check. Another boundary condition is needed for coolant. Insert boundary condition, atmospheric pressure at this end of water. Green check is done. Now we can do one thing. For the coolant jacket, we can consider that heat will be transferred from here to the atmosphere by convection. So convective heat transfer coefficient we have to consider. Okay. So boundary conditions, insert boundary condition, and we are considering real wall with a convective heat transfer coefficient of 60 watt per meter square degree Kelvin. And temperature will be 30 degrees centigrade. you have to select that cooling jacket. So you have to go back to the model again and select that cooling jacket. Selected, green check. So all the boundary conditions have been applied properly. Next one, we have to select some goals. At the same time, we have to find an equation goal to find out LMTD, that is logarithmic mean temperature difference, that is required to find out the effectiveness of this single pass counterflow heat exchanger. Okay, now goals. To find out some surface goals, we want to find out average temperature of fluid at the exit of ethanol and at the exit of cold water also, both to be checked. First one, we are checking for exit temperature of ethanol. Select other, lead number 7, green check is done. This goal we can rename it as average outlet temperature of ethylene. First goal is defined. Now to select second goal. Goals, insert surface goal, average temperature of fluid for the cooling water. To select this location, select other, lead number 6. You can rename this one as average outlet temperature of water. Two goals have been defined. Now we want to have our equation goal, that is LMTD. Okay, let's view the model in isometric form. Finally, we want the equation goal to find out LMTD. Goals, insert equation goal. To find out the LMTD, we have to select the boundary conditions and the previous goals also. Let's select the previous boundary conditions. It will come from initial boundary conditions: inlet mass flow rate of ethylene, temperature, that is the inlet temperature of ethanol, minus outlet temperature of water. Outlet temperature will come from here, bracket closed, minus outlet temperature of ethylene minus, we have to go back to the boundary condition again. Temperature of cold water. All this one divided by ln of, let's copy this part again, paste, bracket closed, and again here instead of difference it will be division. This is the equation for LMTD. This is done. So all the goals have been defined properly. Now let's run it. Let's see the solver window. Machine is going on. Iterations have already been started. Let's the iterations move on. We'll see the results and analyze it whenever it is finished. The solver is finished. We can see our results from the window itself. We had 3 goals. Let's see the goals. It will be in the form of graphs. We can see the first one line is the excitant temperature of ethanol, and the green one is the exit temperature of water, and mid one, this is the LMTD. Okay, the equation first one, that is the temperature of ethanol at the extreme end, it has come down to 32.43 degrees centigrade, and for water its temperature has raised from 10 degrees centigrade to 39.64 degrees centigrade, and for LMTD, final LMTD is 33.78 degrees centigrade. Okay, this is the results we got from the solver window. Okay, now let's see the different results in the form of cut plots and flow trajectories, etc. Results, cut plots, insert cut plots. We're going to see temperature of fluid across the front plane. Okay, so green check. Now the thing is, we have to make this object transparent, right? So let's go back to the model again and make it transparent for viewing the flow trajectories and the pattern of temperature distribution, etc. Transparency changed. Now we can see the distribution of the fluid temperature throughout this heat exchanger. You can see at the beginning, this is the entry of ethanol. Ethanol was passing from the entry at a 78 degrees centigrade. As it is approaching towards its end, its temperature is reducing because of cooling, and from here we are providing water at 10 degrees centigrade. It is passing water from here and it is passing through this passage, and finally it is coming down here. Right, this is the passage. You can see the cold water temperature is also increasing from 10 degrees centigrade, and finally it has come down in the blue range, that is in the range of 30 degrees centigrade near about. And for this ethanol, its temperature initially it was 78 degrees centigrade, and finally it has come down in the green zone, that is near below 46 degrees centigrade. Right, this is the cut plot. We can see this one in the form of an animation also. Let's see cut plot in the form of animation. Cut plot 1, clear and hide. Cut plot 1, play. See the flow of both the ethanol and cold water also. You can view this one from right plane also. Let's change this one. Cut plot 1, clear and hide, and we can edit this part. We can view this with respect to right plane. Let's see that one with respect to right plane. Green check. You can see the temperature at the inner side, it is red, it's very high, and as it is going towards the periphery, it is reducing. Right, we'll see this one in the form of an animation also. See how temperature distribution is changing as it is coming to the extreme right end, that means it is becoming completely red. Is high end, there is an end with hot ethanol, and at the extreme left end is cold water. Better to view this one from the side. Okay, let's clear and hide this part. Now I want to see surface plot. Insert surface plot, and we want to see throughout all the surfaces. Green check. And the thing is, the leads are not transparent, so we cannot see it properly. Let's make the leads also transparent. So it is red zone, that is a high temperature. When here also you can check. Let's make it transparent. Now it is clearly understood that from here ethanol is passing at 78 degrees centigrade, is very high, and as it is approaching towards this extreme left end, its temperature is reducing, and finally its temperature in the range of, like you can see, it's light yellow, green and red also, right? So at the periphery temperature is different. Even for the cold water inlet, temperature is 10 degrees centigrade, and as it is passing across this exchanger, and at the extreme right end, its temperature is in the range of 30 to 46 degrees centigrade, is green zone, right? Okay. Surface plots, clear and hide. Flow trajectories, insert. Instead of number 20s, we will make it more, maybe 60. And instead of pipes, we want to see in the form of arrows only. We have to select the locations of these passages. Let's select the entry of ethanol. Select other, lead, one selected, and also we want inlet of cold water. Select other, lead number 5, selected, green check. Let's see the passage. Okay, it is passing, but it is not showing through this one. Let's edit this path. Flow trajectories, edit definition. We have to select this path also. Select other, lead number 6, done. Green check. It is showing this path also, right? Now I want to see the particle trajectories. Okay, and the particle size is very small. Is okay, we can make it a little big for better viewing also. Let's make the size a little bit bigger. Flow trajectories, edit definition. Let's make the size a little bigger. Green check, done. Now we'll show in the form of animation. Flow trajectories, clear and hide, flow trajectories, and play. Let's see the path. It is clearly visible that from this end red particles are flowing. That means temperature of this ethylene is very high, it is 78 degrees centigrade, and as it is approaching towards the extreme left end, that is at the outlet, its temperature is reducing. Similarly, for cold water at this end is passing at 10 degrees centigrade, that means green flow patterns are visible, and as it is approaching towards the exit, its temperature is increasing. in the blue zone. The particles or these arrows are having color blue and green. That means its temperature is in the range of 30 to 46 degrees centigrade. Right? Even from the particles color, we can understand the temperature of that specific location. It's better to see this one from that front plane. By zooming, we can see this is the inlet of ethanol. The ethanol particles are moving at a temperature of 78 degrees centigrade, and as it is approaching towards the extreme left side, its temperature is reducing. We will show the left side. Here is as the left side, its temperature is reducing, and it is in the range of green and yellow. Right? That means its temperature in the range of like you can say 40 to 50 degrees centigrade. Similarly, for cold water, at the entry of cold water, it is having temperature 10 degrees centigrade, that is blue zone, and as it is approaching towards the right side, its temperature is increasing. You can see the blue arrows are being converted to different color. From blue is converted to light blue, and then finally it is again in the range of blue and green. There is a mixture of blue and green in temperature. That means its temperature is in the range of 30 to 45 degrees centigrade. Okay, this is the flow trajectories of these fluid particles. Next one, we want to see our goals. From goal plots, insert goal plots. We want to see all the goals. Show. It is showing all the results what we have already seen before from the solver window. It is showing that the inlet temperature of ethanol was 78 degrees centigrade, and while passing through this heat exchanger at the extreme left end, its average exit temperature is 39.65 degrees centigrade. That means its temperature is 50% reduced. Okay. Similarly, for cold water, initial temperature was 10 degrees centigrade and exit temperature of cold water 33.78 degrees centigrade. That means it has increased by 3 times, right? Similarly, for equation goal, that is, we find out LMTD, its value is 32.24. Okay, these are the results. We can view this in the form of graph also. That is better. See from the history. That means fluid temperature of ethanol was 78 degrees centigrade, and finally after 120 numbers of iterations, it has come down in the range of 39 to 40 degrees centigrade. And for cold water, initial temperature of cold water was 10 degrees centigrade, and after 120 numbers of iterations, its temperature has increased to 33 degrees centigrade approximately. Okay, and similarly, you can see the LMTD, that is for finding effectiveness, logarithmic mean temperature difference. Final value is 32.5 approximately. Okay, these are all the results what we found out from our goals. We can do some other things also. We can go for optimization of our results. We got our LMTD value in the range of 31 degrees centigrade. We want to optimize the results. That means we want to optimize our LMTD value by changing our input variables. We can do that optimization on another video. This is very simple CFD analysis for finding the effectiveness, or you can say like LMTD of a single pass counterflow heat exchanger. This is all about today's CFD analysis of a single flow counterflow heat exchanger. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.